Good day all. Today I'm going to be speaking to you about basic derivations and integration that we use in mathematics and how these can apply to some equations that we know and use in an every day-to-day basis. Okay, so let's first look at the basic derivative method. Just a disclaimer that this is the most basic method for derivation and integration like possible, is that there are way more complicated examples that use more than one variable, but that's not going to be covered in this video. This is just going to basically go over what the basic derivation method and integration method is and what those actually mean in terms of mathematics. Okay, so let's look at the basic derivative method, okay? So you get d over dx, x to the n. Okay, so x to the n is the original equation, guys. Okay, so what they're doing there, that d over dx before the x to n is meaning that they're asking you to derive that. And the method of doing that is that you take 1 and you minus it from the exponent at the top, and then you multiply the original exponent to the base. Okay, so for example, let's say we had 2x to the power of 4. Okay, and we needed to derive that. If we needed to derive that, okay, so first things first, we're going to take 4 and we're going to multiply it by 2, so we get 8x. Okay, and then we need to still subtract 1 from the exponent, so it becomes 3 at the top. So the derivative of 2x to the power of 4 would become 8x to the third. But what does that actually mean? What that actually means is that at that point of the graph, so if you were to substitute the value at a point of a graph, the x value, so let's say, you see on this point here, let's say that that is the point 2. If I was to substitute 2 into my derivative equation, it gives me the gradient at that point. So you see there, was the point there? It's the gradient of, it's how much that graph is moving up or down at that moment. So that's what the derivative does, okay? Now for integration, okay. The basic integration method is basically the reverse of what you just did there. So you see we have x to the power of n here. The integration, that's what that symbol is there, the little squiggly s thing, the long elongated s. The integration of x to the n, what you do is that you first divide the whole thing by n, and then you add 1 to the exponent at the top. Okay, so let's look at an example like that. Let's use the same one. Okay, so we have 2x to the power of 4. Okay, first thing we do, okay, is that we put 2x over 4, because that was what was the original exponent over there. So 4 was the original exponent, and now we need to add 1 to the exponent at the top. So it becomes 2x to the power of 5 over 4, or half of x to the power of 5. And what that actually means is that the integration formula is basically moving a step up, where when you're deriving, you're moving down, you're moving from the graph to the gradient of the graph. Now you're moving from, you have the graph, now you're working out the area under the graph. And now you can see in this picture, you see anything above the x-axis, we add to the area, and anything below the x-axis, we subtract from the area. Okay, so that's basically what integration is. You'll probably learn a lot more about it if you go further in math one day, but for matric, you don't really need to know integration. You need to become more familiar with the basic derivative method. So what I'm going to show you now is how we can use this to actually apply to everyday equations we have. So I already went through this with you. Okay, so we have the area of a circle here, okay, is equal to pi r squared. Okay, if we had to move back a step, okay, so area is everything within the circle, okay? The thing that's a step back would be your circumference, because that is the total like length of the thing around the circle. So it's the length that the circle encloses, okay? And now we can actually get the circumference of this equation by just deriving this formula. So we take the 2, you see it as a 2 exponent, so we put a 2 at the back because that's the rule. It says here the n goes to the back. The 2 goes to the back. We leave pi where it is because pi is not a variable, it's a constant. Then we take r, and then we subtract 1 from the exponent. So it's just r to the power of 1. I'm not going to draw it in because r to the power of 1 is r. And that's how we get the circumference formula. So it's 2 pi r. We can also use this for volume, okay? So we have something here like the volume for a sphere, okay? What is the thing that, um, if we were to move it one back, is that we have the volume. Now what's one back from that? It's the surface area of the thing, because that's the total area that encompasses the volume, okay? So we have 4 over 3 pi r to the 3. Now we just derive it again, okay? So we have 3 as the exponent, and we have 4 over 3 there. We go 3 times 4 over 3, which gives us 4, okay? And then we have pi, because pi is a constant, and then we have to subtract 1 from the mean to get 4 pi r squared. And you see, it's simple things like this that allow us to derive, is that if you have the formula for area or the formula for circumference, you can derive or integrate to get the formula. If, let's say, you're in a test and one day you remember what the formula for area is, but you can't for the life of you remember what the circumference formula is. All you do is that you derive it, and there you get the circumference formula. But just remember that this only works for area and for area and volumes with one variable. So we can't do things like areas of rectangles or areas of triangles, because they have more than one variable. They have the length and the base, or they have the length and the height, or the base and the height. So that's more than one variable, and we have to use more complicated integration and derivative methods to do that. I hope that was a good explanation of what this thing was about. I will look forward to seeing you guys next time. Thank you.